Hi everyone, I am Shiv Prakash, Research Scholar, Department of Electrical Engineering. Let's start the session. Some question number first. A fixed frequency PWM ideal buck converter switching at 500 kHz at SD state draws 20 watt from a 10 volt input supply. The filter inductor of 147.2 nano Henry is used to restrict the peak to peak output capacitor current ripple to 10 ampere. Peak to peak output capacitor current, it means inductor current same because of same current flow the capacitor ripple current. The load can withstand the maximum voltage of 5 volt and the output voltage is 5 volt. If the same converter is operated with the constant on time control with the constant on time of 0.2 microsecond, the switching frequency has to be it means how much the switching frequency in second case and the same converter operated is the constant on time control method. Okay, he says the buck converter. You know the buck converter ripple current. Delta IL is equal to Vs minus V naught into D divided by FL, and also you can change this D equals to 1 minus D V naught sorry, this one Vs into D Vs is equal to V naught by FL, and delta IL is given 10 ampere. Take it equal to 10 ampere and put the value, then you find D is 1 minus D equal to 10 into F into L divided by Vs. Vs is also given as 10 volt. Frequency is given 500 kilohertz. Inductor 147.2 10 to the power 9 by 10. You calculated of this 10 to the power minus 9. Calculate, you find the value of 0.0736. Then you solve the quadratic equation. D square minus D plus 0.0736 is equal to 0. Then you find the two value of the D. First one, find D1 is equal to 0.08 and second D2 is 0.9. And you can also know about the output voltage. Output voltage is equal to dVs for the buck converter. It means if you put the value of 0.92 in this one, means 9.2 volt, you give the supply 10 volt. This one the much higher duty ratio. This is not consider for this. This one you can't consider. You consider like D1 is equal to 0.08 and output voltage that it means output voltage is 0.8 volt. Next condition say that the load can withstand the maximum voltage of 5 volt if the same converter is operated. Maximum volt 5 is given. That it means if you use this duty ratio, then maximum voltage is given 9.2 volt. That's why is also given for the load voltage, maximum load voltage 5 volt. You can choose the 0.08 duty ratio. the load can okay, the same converter is operated at constant on time. Constant on time, it means dt is a constant. Dt is on time. It's also given that 0.2 microsecond. D2 ratio is the same, 0.08 volt. Sorry, 0.08 into t, 2 microsecond, 2 into 10 to the power minus 6. That's why find t. T is equal to 0.2 divided by 0.08. 10 to the power minus 6, 1 upon 2.5 into 10 to the power minus 6 is asking about the frequency. Then you find the frequency, f is equal to 1 by t. If reverse of this, then you find 400 kilohertz frequency. Okay, go for the second question. In which of the following cases the inductor current ripple is independent of on input voltage? It means if you change the input voltage, then inductor ripple is same for all the input voltage. Then option is given is peak CMC buck converter, valley CMC boost converter, constant on time buck, constant off time buck. It's like that. It means buck and boost. Two condition is there given here. Peak CMC and valley CMC both are the PW1 converted, means frequency I think fixed. You can change the frequency, then this option is not considered for this. This one is not correct. And C, D, E, F is can for the answer. Okay, I use this one buck. You know about the buck converter? Buck converter d2 delta IL is equal to Vs minus V naught divided by into D by FL. And you can, if you change the Vs, then you find the D into 1 minus D. So you can V naught by V out is equal to dVs, you know, and Vs equal to V naught by D minus V naught divided by FL. Then you can't replace the D in this function. That's why the for PWM converter you say the input voltage independent because of the iteration frequency also is. If frequency will change, then the delta L acceptance. That's why I will not consider this. First of all, you know about the buck converter T on T of time here given. If you draw the buck converter, then you find like ES B naught C L. So switch this one D. Apply the here the for Bole second equation, Bole second balance equation. Then first when the switch is on, then find the Vs it means VL into T on plus VL into T off where total time period is equal to 0. This is the volt second equation. Then with T on, then you find the Vs minus V naught into T on divided by T plus you find it into T off, then you find VL is equal to minus V naught. T off divided by T is equal to 0. You find V naught is equal to Vs into T on divided by T on plus T off, the output voltage. And then when you find the delta IL for the buck converter, delta IL is also given in the voltage term Vs minus V naught divided by T on divided by L. Replace the Vs here, then we find T on plus T off into V naught divided by T on minus V naught total T on divided by L. T on is going to change this way, T on, and then V naught and T V naught T on both are cancelled here. Then you find V output into T off. You can also find T on cancel out here, this one, and divided by L. This is delta IL for the buck converter. Once again, I draw for the boost converter. If you draw the boost converter, then you find Vs plus minus V naught C L Q D. Apply same volt second equation. VL T on plus VL T off divided by T equal to 0. When switch is on, then you find the same Vs is Vs into T on plus when switch is off, then you find Vs minus V naught is the VL divided by T is equal to 0. Here to find V output, V output is to Vs T on plus T off divided by T off. And you find delta IL in here. Delta IL you find if the switch is on, then current will increase here, then voltage Vs is up here, then Vs into T on divided by L. You replace the Vs here, then you find V naught T off into T on divided by T on plus T off divided by L. This one for the boost converter ripple current. let's see the option constant on time buck. It means on time constant. Here buck is not present here. If constant on time, it means off time is varying. Now time varying, delta IL also varying. This means this option is not correct. Second, constant on time boost. For the boost, you need both on time both controlling. That's why I delta IL is a constant. Neither is not constant. Then for boost will not say constant off time. For buck, here the constant off time. So off time constant, then output also constant. Given the reference and delta in the inductor is find in design. When you want to design the inductor, then L is constant, then delta L also constant, and this option is correct. Our next question, a non-inverting buck boost converter, so in the figure, is driven by a current hysteresis control using a hysteresis band delta I. Delta I is the same as the ripple current. What will be the expression for of the its hysteresis switching frequency? In the option. First of all, you know about the buck boost converter. For buck boost converter, V output you dVs divided by 1 minus D. Here you find the duty ratio. Duty ratio you find V naught divided by Vs plus V naught. And delta IL is equal to Vs. Second question, I think option number E, constant off time buck converter. Because of the here, you know, you see there delta IL is equal to V output into T off divided by L. Here the output voltage also constant and off time is given constant, inductor also constant. That's why if a voltage change, input voltage is independent is the inductor current. And for buck boost converter is also dVs of IL FL. Replace the D here. The delta IL is same as the delta IL. Delta IL into L into D is equal to V naught divided by Vs plus V naught. And find frequency V naught Vs divided by V naught plus Vs into 1 L into delta L is the frequency. Which of the option is correct? I think first option correct. V in V naught plus V owned by L delta L. Okay. Which of the following method provide lowest efficiency under light load condition? Pulse width modulation, pulse frequency modulation, pulse skipping modulation, burst mode control. Here the pulse width modulation in PWM condition control. Here you give the fixed frequency. If you give the fixed frequency and the load is reduced, then in this condition the switching losses is greater than the conduction loss of the switches. That's why a pulse width modulation is given the lowest efficiency for light load condition. That's why you use the pulse frequency or pulse skipping modulation for the light load condition, in which the conduction losses and switching losses both are reduced. But if a pulse width modulation, frequency losses is fixed by the frequency you can given. That's why this one is the lowest efficiency for the light load condition. And question number 5, match the statement of column A with the statement column B. Current mode constant on time control in boost converter. Current mode constant off time control in buck converter, and current mode constant on time in buck converter. It means boost converter is given on time control, constant on time, and buck converter is given the off time control and on time control. Okay, further here you given the method to provide lowest efficiency under light load condition. In light load condition, you know about the frequency switching losses. If you find a switching loss, P switching loss, VIF, I think not so when the switching loss is depending on the frequency directly, that's why the frequency is fixed in pulse width modulation. If you give the load is light load condition, that's why losses are same for the light load and high mode heavy load also. That's why the efficiency reduced in the light load condition because of conduction loss is reduced because of current is reduced, but switching frequency is the same because of power in switching loss directly proportional to frequency. That's why the frequency, that's why this power loss is increases in the pulse width modulation because the frequency is fixed. But if you use the pulse frequency modulation and other mode control modulation, then you find the frequency also vary depending on the load condition. If a load is reduced, then frequency also reduced, and load is increased, then frequency also increases. That's why the other controller is best for the light load condition. But when the pulse width modulation you use, then frequency is fixed. If frequency is fixed, then losses is directly proportional to frequency. It means the conduction loss depending on the current flowing through the switches on time conduction loss. But frequency is fixed. That's why the losses is switching loss is greater than the conduction loss in this condition also. That's why this is a poor efficiency pulse width modulation. In current mode control, constant on time and constant off time. Constant on time, it means the trailing edge modulation. It means the given the Bailey current mode control because of the on time control, but the off time is varying here. If you know the trailing, sorry, constant on time it means the off time is varying here. If you, I'd rather both the trailing edge and Bailey edge. This is the pulse frequency. So inductor current. Modulation signal. You give it. You see the here peak CMC. First I will choose here. Because of the peak edges occurs here, that when the turn off turn on condition. That's why it is known as peak CMC, peak current mode control. In this you see that this, when IM greater than IL, the output is given here because of in RS flip-flop condition, IM connected to the RS and switching frequency connected to the S. When the R is greater than S, then you given the peak, it means the duty ratio here. That's what happen here also. In this we observe that this one is depending on the ripple current, this position. This one will change, then this one also will change. It means it's not fixed, but here the off time is fixed given. If you change the this one, and off time is fixed, this one is known as the off time control, constant off time control. Because of this one is not fixed, it will change depending on the frequency. If the frequency will change, the D also will change for given the constant output voltage. If frequency is changed and duty ratio is not changed, this means the output variation given here, and this one is known as constant off time control. Same we draw for the Valley CMC. This one frequency. In this here we use this IL and multi signal like that is IM. This is the Valley edge condition. Peak CMC, this one is Valley CMC. Really IM is connected to the S flip flop in S and set, or and IL connected to the reset when the S IM. M reached to try to more than the IL, this condition, that's given the output. And is here given the when the pulse is provided to the R, this means R is a high, means reset condition, flip flop condition, this one is 0, this one also high. This is condition is the, this one can depend on the this age and this Bailey CMC is known as the constant on time. This was not very, this one dependent on the, no, I think this one is constant. That's here I am here we are controlled given the frequency given here, that's why this one is now off switches, this switch control here, and here control by on. This means constant on time is the Valley current mode. I think C is for the buck boost converter, and this one is such a frequency restricted for this one is input is 5 volt, output is 8 volt. It means this one is boost converter. This one is boost converter, then you apply it for the ask for the frequency. The delta IL is given, then you find delta IL. Delta IL is for Vs to T on by T. This is D divided by L. Everything is given. Find the frequency. Frequency delta IL into T on and find frequency. I think frequency if you solve this, so you find frequency approximately 300 kilohertz. Button C and D. Current mode for constant off time control. Off constant time control is a peak control mode, and current mode constant on time in the buck converter. Constant on time is same on time is in the belly current mode control in CMC. And output capacitor ripple is also given. This one for the buck converter, P in greater than the V naught here. Delta IL also given here. If you find delta IL, same apply for the condition. Delta IL for the buck converter, then you find this current. I think V naught minus Vs minus V naught is in first condition. And after you use, then you will connect with after. An ideal buck converter, the parameter is shown below. This one is buck converter. I think something is missing here. This one is given some monostable timer is given here for the on off control in this box. And this will be 1.8 microsecond. Is not mentioned here. He is asking about the inductor. If the capacitor current peak to peak must be considered within 5 ampere. It's not more than 5 ampere. Capacitor peak current, it means you know in the buck converter is same as the capacitor ripple current is same as the inductor ripple current in the buck converter. And you find the buck converter here. This one IC capacitor current. If you find same current given in the inductor, also flow inductor, but here is the positive negative is the same in the capacitor current, because of capacitor average current is 0. That's why is given the capacitor current peak. Peak means is 0 to, not given the peak to peak, so given the peak. Peak means this one 0 to 5 ampere. If you find delta IL is 2 times of this peak. Delta IL is equal to 10 ampere. But is given the not more than, consider within 5 ampere, it's not more than 10 ampere. And delta IL is a buck boost converter. The frequency also not given here, that's why you can't apply that type. This one for the PWM converter, in frequency and frequency is fixed, but given the on port. T on plus T off, you know about the time period, total time period. V output, you know, Vs into T on divided by T is D due to ratio. Yeah, capacitor peak current is given. Capacitor peak current is same. Capacitor current, ripple current, and inductor ripple current is same in the buck converter. If you observe the buck converter here, then the same current flow like here also. But the average inductor current, in average capacitor current is 0. That's why the average output current is flowing same as the inductor current. But you observe the ripple is same as the inductor ripple current and capacitor ripple current. If you this one is the, if you take a inductor current, then same is flow in capacitor also, but is this one is average is 0 in the capacitor current, because of you see the here IL is equal to IC plus I naught. When you take the average, if you take a average current, the average is IC average current is capacitor average current is 0. For the find the charge second balance, if you know the also applied current second balance, is also known as the charge balance. And the capacitor inductor is the flux balance, and the capacitor is like the charge balance. Charge balance is when how much we charge, that's energy also discharge in the some time period, because because the average of the inductor current and average of the average of the inductor voltage and average of the capacitor current is the same. That's why this one 0. If you this one, the ripple is the same flow from the capacitor and inductor. If you is this one given is capacitor current peak means 0 to 5 ampere. This one is given in the question. This you take the ripple, total ripple is same as the inductor total ripple current is on the 10 ampere. Here inductor value is not given, that's why you can apply this formula also here. Like he is asking about the inductor current, and if you find the duty ratio and frequency, then the frequency is not given, but we give the only this one constant of on time, but he is using the not get here, that's we find that this one is a constant of time current. First to find a d is given, Vs is equal to 10 volt, and V naught if multiply the average output current and resistance, then find 1 volt. V is equal to 10 volt, V naught equal to 1 volt, then find d is equal to V naught by Vs 0.1. It is given off time. This is used for the on time control, but is not get connected here. That's when this connected in the off time. Off time is given almost 1.8 microsecond. Off time we know about dt. D is 0.9, then 0.9t. Two microsecond. If t find, then on time, down time is dt. The switch is on, then d is equal to 0.1, 0.2 microsecond. Then apply delta IL. Delta IL is equal to Vs minus V naught divided by FL into T on. Delta IL not much, the 10 ampere is given. That means this one is maximum 10 ampere. Yes, you know 10 volt minus V naught is equal to 1 volt. Sorry, if it is not present here, if you use the T on, actually you use the dt, then if you duty cycle, then you find the D in FL. If you directly use the T on, then if it not here, and T on is given 0.2 microsecond. Then is should be greater than 9 into 0.2 10 microsecond. Sorry, this one L. Henry, microhenry. 2.818 microhenry, or L equal to 180 milliamp. millihenry. See the option. Sorry, this one 19 microhenry, that means this one 180 nanohenry, not really nanohenry. Is greater than 180. They are greater than 180 means approx the used. Then here 180 also given, but 180 you can't choose. You can choose the 185 nanohenry greater than the 180. 180 is the boundary condition. That's why you will choose the one greater than 180 and 185 nanohenry. Next question. Consider a symmetrical circuit peak to peak symmetrical swing of 24 volt. This one plus 12 volt and negative 10 volt. 24 volt the swing. The input voltage is given apply to the inverting input. Inverting is given is the negative terminal. Is a symmetrical sawtooth waveform of average value 0 is given in the input signal, has a positive slope and has a peak to peak voltage of 20 volt. The average value of output voltage is asked. First of all, as we trigger, we working on the hysteresis loop. We find create a hysteresis loop in output given between the upper limit and lower limit. Then first of all, find what is the upper limit. If you see the circuit, find this one voltage. This one voltage, you find this current flow like that. So V0 into 20 kilo divided by 60 into V0 by 3. Now find the upper limit of the symmetrical hysteresis loop. And upper limit maximum voltage is the saturation voltage. If you, I will take V0 is equal to V saturation and V0 minus V saturation are given in the output signal. And I choose, I let the, if the V0 equal to V saturation, then what happened? What the upper limit gain from the here is V saturation into this one resistance divider you taken 20 divided by 20 plus 40. V saturation divided by 3. If you take a V saturation 12, then you find 4 volt. Same if you choose the output voltage, take minus V saturation, then you find lower cutoff, then you find minus 4 volt. It means plus 4 volt to minus 4 volt is the lower cutoff of the hysteresis loop of symmetrical. This one V in, this one V saturation, this one is the V output. I will take V saturation here, minus V saturation, this one minus V in. Upper lower, our lower limit is minus 4 volt, upper limit is given 4 volt. draw the waveform for the given sawtooth wave. So I think sawtooth wave, symmetrical sawtooth wave, average value 0. Average value 0 means negative and positive both present in waveform. Have only positive slope, not negative slope. In triangular wave, you see the positive and negative slope both are present, but in sawtooth wave, the negative slope is not present. Peak to volt 20 volt. Sawtooth wave like that. This one provide plus 10 volt, given this one minus 10 volt, and reference signal also given here. Take a reference signal, plus 4 volt, minus 4 volt. Yeah. In Smith trigger, we will take for the positive slope. Positive slope is given to negative to positive, like that. This on the cutoff area for plus 4, minus 4. This one for the positive slope. If negative slope is present here, this will go like that, negative slope like that. But if negative slope is not present here, then take only positive. Positive V output is given between when the input signal greater than minus 4 volt to plus 4 volt. This one is 0, like that. Output signal given between the minus 4 to 4 volt, then you find the output. And see here, when the input signal greater than minus 4 volt, minus 4 volt means less negative to the reference, and this one to plus 4 volt. This one is given in the output, like that. This one is T and 2T. Find this time period for the output. If you see the here slope, first to find the slope is given. Total y-axis is 20 volt and time period totally t. This one is slope 20 by t. Then what time of signal is present? So minus 4 volt to plus 4 volt. This So we take T on, total 20 volt in the T time period. Then what time period for the 8 volt, means 8 divided by 20 and 8 by 20 T. The T on is 8 by 20 T. Then find V output. V output present here only. Then plus signal is present, plus we have given the positive slope. This one is 12 volt is given, and this is greater than difference signal here. The 12 volt given the output, when the negative slope is present, then minus 12 volt is given in output. That's why this one is 12 volt. And 12 volt into how time period is present, 8 by 20 T divided by total time period is the average. .8 volt in the output. B of C. Question number 8. The output voltage of an ideal boost converter is to be regulated at 12 volt by constant on time current control mode. The input voltage can vary from 3 volt to 8 volt. The value of inductance is 2 microhenry is given. First of all, I written this 2 microhenry. V in vary from 3 to 8 volt. V output given 12 volt. The worst case inductor current ripple. Worst case means it means delta maximum ripple in inductor ripple current is given 4 ampere. And also given a condition, the maximum switching frequency is given the converter. In other case, both are I think different cases. First, given the maximum, we take the inductor ripple current, then here is also given constant on time delta IL. For the boost converter, you know Vs into T on divided by inductor Vs by L. Is given maximum delta IL maximum when the Vs is maximum. Take it. Then find here T on. T on delta IL is given 4 ampere. L inductor also given 2 microhenry. At Vs is 8 volt. Find 1 into 10 to the power minus 6 second. This is the on time period. Second question is asking about the maximum switching frequency. When maximum switching frequency occurs, then find the output voltage. Boost converter. Boost converter output voltage is equal to divided by 1 minus D. D means T not T on by T. Then here find 1 minus T on by T by V naught. frequency V naught minus Vs divided by V naught. You can ask in the maximum frequency. Maximum frequency occurs when the Vs is minimum in this condition. When Vs is minimum, the frequency will be maximum. V naught given 12 volt, minimum V in 3 volt. T on also 50 kilohertz. The maximum switching frequency for the output voltage is constant 12 volt and input voltage vary from 3 to 8 volt. Question number 9. For a DC-DC converter, shown in figure, this one is a buck converter. On state resistance R1 given of MOSFET and diode voltage drop is given 0.8 volt and neglecting switching losses. The power dissipation in the MOSFET will be. Is asking the power dissipation in the MOSFET is given the switching losses. Switching losses is neglected. It's only conduction loss is present in MOSFET. The conduction loss occurs when the MOSFET is on, and on resistance also given. Then we find the on time current and resistance also given, and find the power dissipation. Frequency also given. I think D2 ratio is given D 0.4. I read rather circuit further explaining this in more detail. Switch is given. This one is plus, this one minus, further convert this that also represent. Inductor resistance not given, then you can take inductor as the ideal inductor, and capacitor also not given. Capacitor resistance, sorry. Vs, this one V naught, this one given R, C, L, this one RSW I taken, VF I will taken. First of all, find the output voltage. When the output voltage we find, then output current we know. When output current is low, then you can also find the input current. And when the switch is on, same current flow in the switches. And you can't apply direct formula via output is equal to dVs, because of the this is not ideal, and resistance and voltage drop are also present. That's why you find the average volt second equation for the inductor voltage. So VL on time, this means duty ratio d dt plus off time 1 minus dt divided by total time period equal to 0. This is the volt second equation for the inductor voltage. And find inductor voltage when the switch is on, the switch is on, then this one is closed, the current flow like this. And same current flow IL, because of this one is off, this current also flow the IL of the, and use the KVL. In this condition you find VL is equal to Vs minus V naught, written directly IL into RSW with this resistance present here into D. So this is not TT considered for the first plus VL when the switch is off. The switch is off, then we find this one is on diode, then same IL inductor current flow like that. Then we find VL is equal to minus V naught minus VF into 1 minus T equal to 0. Solve the equation. dVs minus dV naught d IL into RSW minus V naught minus VF plus dV naught dVF is equal to 0. dV naught cancel out, then find V naught dVs minus d IL into RSW plus VF 1 minus d. If you take average inductor current for the buck converter, IL I naught given as a V naught by R. Replace the IL here. V naught is equal to dVs minus d to V naught by R to RSW take V naught here and take V naught common and find dVs minus VF 1 minus d divided by 1 plus d divided by R. With all of quantity given, Vs also given, duty ratio also given, and RSW is a switching resistance given, total output resistance also given, I think this one 1 ohm. Put all the value here, then you find the output voltage. Output voltage is 9.37 volt. You solve this one. Then I0 is also 9.37 divided by R is equal to 1. RMS current, switch RMS current is same as the input current. When the switch is on, I will take a waveform. Are the average all current. This one I0 average current is equal to IL, same as in inductor average current. Switch current, when switch is present, then this current also flow like that. Average switch current. For dt, this will be t. Then find ISW RMS to I0 into root d. Dt by t, you find the dt cancel out. And I0 is given is 9.37 to root 4. We find this one is 5.789 ampere. Power loss ISW RMS current square into RSW RMS given 5.789 square into 0.04 ohm. Even RSW, calculate this, we find 1.4 ampere. Oh sorry, 4 watt. The power loss at the switches. Participation means power loss. Okay, I think this is the last question. Thank you to everyone. And you can also watch this video on the YouTube or later.